Yeah, hello. I'm Chris Rackauckas, and I am a research affiliate with MIT. I'm also the VP of Modeling and Simulation at Julia Hub. And what I want to talk about today is how compiler smarts can be integrated into numerical methods in order to be able to improve the lives of people who do numerical computing. So specifically, I'll be talking about NonlinearSolve.jl, but this applies to a lot of other of the Julia tools within the SciML ecosystem that I'll describe. So what is nonlinear solving all about? Well, it's about finding roots, right? But I'm not talking about these kinds of roots, right? This is, it's not roots like vegetables and whatnot. The roots that we're talking about when we use a root finder, right, is solving nonlinear systems of equations, right? So it's, for example, finding, what are the values of x and y that make a certain system solve, right? And so here's nonlinearsolve.jl, right? You might be familiar with R, MATLAB, or Python, or whatnot. But here's nonlinearsolve.jl. It works in Julia. You define your function that says, I have x and y. I have these two equations I want to satisfy. You move everything over to one side. You say, okay, this needs to be equal to zero. This needs to be equal to zero. You give it an initial condition, and you give it you define the problem from that, and boom, when you solve it, you get you get your solution, right? You get x and y that solves this. So okay, therefore, that's all you needed, right? This is what you had before. This is the Julia version of it. We're done, right? But it turns out that you don't need to just do simple cases like what's shown here. Not everything in this world is simple. So there's a lot of other cases that need to happen. So for example, what if I need to find where a ball bounces onto the ground, right? Then you're effectively finding where does position of t equal to zero, right? So there's other cases that need to happen with nonlinear solvers, and there's also, it can get very complex. So everything to do with chemical reaction systems, macroeconomics. You can always describe what an equilibria is as forward rate equals reverse rate. Find all of the variables and all the parameters such that everything equals zero, right? So it turns out that not everything is this simple world. We might need tooling that extends us and scales us to very difficult types of root finding problems, right? And so that's really what nonlinear solve is all about. So and so what makes nonlinear solve special, right? I think that a lot of people look at this and go, okay, I have a Newton method in Python, I have a Newton method in R. This is the Newton method in Julia, right? It's the same thing, right? But I want to kind of showcase how it's a bit special because it does anti-black boxing of code. So say, for example, you have this as your representation of a nonlinear system you want to solve, right? Now, the reason why someone who is mathematically and numerically smart might want to say, hey, you might want to say, hey, don't solve the nonlinear system like this, right? So Newton's method has to do LU factorizations, which has O of n cube scaling effectively. And I mean, there's some ways it's O of n squared, details, but effectively, you have O of n cube scaling, and so we have 5 equations, and so it's like 25, or 5 to the third power amount of work, right? And someone who's a smart mathematician might say, oh, but maybe I can come up with a better way of solving this system of equations, so that way I can save on the amount of work, right? But here's the thing, right? Anything that a mathematician can do, a computer can do, right? And so what we're doing with nonlinearsolve.jl is effectively that. So here's a system of equations, and we say, solving a system of 5 equations is much harder than solving a system of 1 equation. So let's transform it. And so what we have is you can say structurally simplify my set of equations, and you can take 5 equations and it'll spit out and say, okay, this is the only equation that you have, and all of your other variables are defined explicitly by these relationships. Here I'm showing this through the modeling toolkit symbolic syntax, but you can also apply this directly to code, right? It doesn't matter if a function is defined by code or symbolics, it can perform these same simplification passes. And from that, then, if you only have one equation that needs to be solved, everything else is explicitly derivable from that one variable, then let's solve for that one variable, right? So here what it's going to do then is it says, okay, I only have the equation in terms of U5 now. Give me an initial condition for U5, and it will build the nonlinear problem and solve it. And here I'll give you a solution to, it's giving you a solution to the system of equations by giving you only a single solution, right? What single value did it give you? Well, it gave you U5 because that's the piece that it simplified it all down to. That u5 is a function here of hypod of u4 and u1, but u1 is just a function of u5. u4 is a function of u2, u3, da da da. It's all just u5 at the end of the day. So what it does is it says, I just solve for u5. And so I give you a solution in terms of one variable, but now you can query it and you can say, okay, what is the solution of the other variables? And if you ask it for the other variables, it'll be able to generate them on demand. Right. And so, this isn't your papa's, Newton method. This is the new kid on the block Newton method, which is really integrating, this symbolic tooling and compiler analyses, be able to bring down, a problem that is, 5 cubed in cost down to 1 cubed in cost. Right. And so it's using a lot of compiler smarts along the way. Now, for sufficiently too large systems, it can be difficult to do this kind of simplification in practice. Though alias elimination, tearing, and such, there are ways that we are working on scaling them. But other things that we can do, for example, involve using automatic compiler sparsity, right? So currently in tools like SciPy, right? They kind of say, like, oh, you're going to come, you want to solve a numerical nonlinear system. Well, I'm going to use a Newton method, right? And if you get to a system that's sufficiently large, it says, oh, either use a Krylov method or give me your sparsity pattern, right? Now, the downside of using a Krylov method is that in order for a Krylov method to converge fast, you should be providing a preconditioner, and those are problem specific, and that's not too easy to do, right? So there's user input to do that. But on the other end, in order to specify the sparsity pattern, right, you kind of have to know, like, oh, hey, for my system, the sparsity pattern of my matrix is this sparse matrix, right? And in some cases that you can write these down, but it's not always trivial to compute what your sparsity pattern is, right? So the way that tools like SciPy and stuff will work today is they just say, I'm going to use dense, Newton's method unless you give me a sparsity pattern. But does that actually need to be done, right? Do we actually have to do we have to put this work onto users, or could we as package developers actually solve this problem for the users, right? And this is where nonlinear solvers auto compiler sparsity comes into play, right? So we showed these algorithms back at a program transformations workshop in 2019, and now we've really integrated them into the whole system, where let's say you have a complicated nonlinear system, right? It can be you can put neural networks inside of there, define a partial differential equation, a whole jiggy jag of difficult pieces, right? There's a general code that goes right here. And what you could do is you could say, build a problem and solve the problem. When you do that, it'll use an automated solver, right? But you can then dig into it a little bit more, and you can say, okay, I want to use a Newton-Krylov method. I want to, and those are the standard things that you'd expect from other nonlinear solver packages. But here you can say is, hey, use automatic differentiation to be able to compute the Jacobian and do auto sparse forward diff, right? And what this does is it uses this algorithm, which you can look up. We described the algorithm. It uses this algorithm to automatically discover from your code what the sparsity pattern should be, right? You can compute this because effectively you know that your sparsity pattern is going to have a 0 only if for all inputs, only if there's no way that input I could affect input J, right? So you really just have to trace through your code. It's a taint analysis to basically say, does this input ever taint this output? So fully automatically, we discover what the sparsity pattern is, and then we apply optimizations which makes use of the sparsity pattern in both the way that the Jacobian is generated and in the way that we do the solving of the nonlinear system. So in terms of the factorizations, and not only that, it also automatically makes use of automatic differentiation for that sparse Jacobian construction. And you can use this also in a ways that also defines an IOU for automating the preconditioners for Newton-Krylov methods. And so this takes what we say is that very difficult part, right? What do you do about defining your sparsity pattern? What do you do about defining preconditioners? It takes this very difficult aspect of the numerical, setup process away from the user and turns it into a fully automated piece through compiler analysis, right? So, I just want this is the core of nonlinear solve and what we wanted to solve. How do you get this to the user? But then the next question that goes along with it is, well, if we just have a standalone nonlinear solve kind of piece, and it just, it just is its own thing, it's not going to be as useful as if it's integrated in with a whole ecosystem, right? And now what we were looking at is, well, there is an ecosystem of equation solvers that does exist within Julia, right? There's these differential equation solvers, there's linear solvers. And so, in the same vein, like how SciPy has everything play together, the Julia SciML ecosystem is building something that it covers bit of a larger domain, and with these kind of compiler enhanced tooling, but in the same way, it all plays together, right? And so I want to kind of paint a picture now of how everything looks in terms of the differential equation solver space, and then say, how do we map that over to nonlinear solvers so that way, all of these compiler smarts nonlinear solving tools now feel seamlessly integrated with the rest of the ecosystem. And so, this has a common interface between optimization, integrals, nonlinear solve, all these pieces that you'd expect within a scientific computing library. I'm going to show you now what some of the stuff looks like, and some of those results we have for differential equations, and how we map that over to then the nonlinear systems, right? So the first thing is that we really focus on speed and performance, right? So in terms of the differential equation solver speed, I think a lot of people have actually seen and tried, some of the Julia differential equation solver tools, and saw about the 50x faster than SciPy, 50x faster than MATLAB, 100x faster than DESolve in R. And there's a lot of benchmarks and details that go into exactly why that's the case. If you're interested in actually being able to, by pen and paper, predict that performance result, I'd say go to the Julia for Biologists paper. It's a Nature Methods paper that has a very distinct description of why we have this performance difference against SciPy, even when numba is involved, right? This number is with numba, right? So there's this performance advantage that we have because of the algorithms, and there's a certain form that we've been taking to be able to get this performance advantage. So what we wanted to do with nonlinear solve is, not just have the compiler smarts, but we wanted to have exactly the same benchmarks should look the same way. Code optimization should look the same way. The input code should look the same way. We should get very similar results to this, because this is one of the pieces that for one of the reasons why we've been seeing a lot of adoption in the ecosystem. And this is a slide then pulled from a lot of the discussions on differential equation solvers, stability, stochasticity, adjoints, inference, and parallelism, right? Everything should work on GPUs. Everything should be able to be differentiable. Everything should, be very robust, right? All of the same things that we have for differential equations, we want to make sure that all of those exist within nonlinear solve as well. So here's a slide that shows the GPU performance, right? So the DiffyQ GPU, the GPU solvers. There's a paper that we have. I forgot to link the paper name here, but if you search for it, you'll find that the approach that we take to doing GPU programming is very different from a machine learning library, in that we directly generate the kernels, right? So we generate .ptx kernels instead of using array kernels, and that ends up being a whole lot faster than the machine learning type of approach. So here we are benchmarking against JAX with its VMAP approach, and we show that it's about 20x to 100x faster. That we're about a 20x to 100x faster over a range of problems with CUDA, and we support CUDA. We support Intel GPUs, we support AMD GPUs, and also Apple GPUs. It also supports the GraphCore IPU as well, right? So this is the kind of thing where, the differential equation has this feature. So anyone kind of coming from the differential equation space, the nonlinear solver space, would expect similar performance gains and similar GPU compatibility. So we wanted to make sure that we kept all these features. And also a static compilation to WebAssembly, right? The ability to take a code that has a solver embedded into it and generate web apps that are fully JavaScript that can do this. So, so that's what we have in the differential equation solver space. So how do we bridge the expected features and the expected form of differential equations and linear solve? How did we map this over to NonlinearSolve.jl, so that way it would have the same experience to a user as the differential equation solvers? So it ends up then being a new part of this set, right? I put it in here in the middle, but it actually kind of the differential equation solvers came first, then linear solve, then optimization, and so nonlinear solve is actually like the new kid on the block that had to kind of map into this existing ecosystem. And what we have is a format that is this kind of, you define a function, you define your bounds or your initial conditions, you define a problem, you define solve. Right? It turns out that every single one of the equation solvers in this form, whether it's integrals, optimization, all the different differential equation types, all of them have exactly the same form. That you define the function that you're going to be interacting with, you define the initial conditions and parameters, you define a problem type, right? And then on that problem type, you hit solve, right? And then same thing. So, but when nonlinear solve, instead of having like differences between ODEs and SDs, in this case, we have different forms of root finding equations, right? So, one form of a root finding equation is the interval equation, interval root finding problem. So, we express this as a interval nonlinear problem, right? So, we have different problem types for the different cases that can show up. And the interval one says, okay, between u being 1.0 and 2.0, the solution to f of up should be equal to 0 within here, right? And now for nonlinear problem, well, this is your standard nonlinear problem, which we consider to be the systems of equations, right? Now there's other interactions then that we made sure to have, so that way it feels seamless with the rest of what we have in the scientific machine learning ecosystem. So for example, if you have an ODE, right? So here's your ODE syntax. Again, you define what f is in your ODE, you define the right-hand side, you give an initial condition and a time span, and you have a problem type, right? So you have an ODE problem type in the ODE case, you have a nonlinear problem in the nonlinear problem case, right? It has the syntax all looks exactly the same. But if you want to convert between the two, right? A very common thing to do in modeling is to say, well, I want to know where an ODE has a steady state. A steady state is defined as where all the derivatives are equal to 0. It's solved as a nonlinear problem, right? So what you can do is you can take an ODE and put steady state problem on top of that, and now it generates this nonlinear problem for the steady state solving equation. And now right here, this is then interpreted as something in the nonlinear solve space, and then you can solve it using any of the options or solvers or methods of NonlinearSolve.jl, right? And so where this happens a lot in mathematics, that there's a lot of connections between different ways of representing problems, right? Where not implicit solvers of differential equations are solving nonlinear systems and all sorts of connections. And so what we've done within the ecosystem is made it so that way you can do these conversions of problem types to be able to much more easily mix and match the different numerical tools you want to employ. And another thing that we made sure to do to make it feel fully integrated with the ecosystem is make it so that way all the options for how do you do the linear solving is using this other library, right? Again, we have these different sets of libraries, and linear solve is what we've been using as the linear solvers within differential equations.jl. All the same choices then exist within the nonlinear solvers. In fact, this option is exactly the same between the ODE solvers, the SD solvers, the differential algebraic equation solvers, and now the nonlinear system solvers for nonlinear solve. And this means that everything that we've done with linear solve, which is a different video, you can go check the JuliaCon, right? Everything that we've done to make sure that we can interface with Pardiso, KLU, UMFPAC, all the different ways of handling sparse linear solves, those carry over into NonlinearSolve.jl, which is something that you don't see in higher level languages very much, right? Higher level languages like in SciPy, you can choose to do it. It's dense versus sparse, but you don't really have a choice between the myriad of different sparse solver, the sparse LU factorization methods out there, which have different characteristics on different sparsity patterns. And so this kind of keeps a lot of flexibility in how you can choose the solver backend to be optimized to different types of sparsity patterns. Now, one of the things that we cared about a lot when building this was it should be fast. And the way that we did this is that we made sure to use a lot of the same principles as what we use within the other parts of the ecosystem. But one of the other interesting things that we found was that we actually ended up pretty robust by the end too. So one of the things that we weren't really expecting was that MinPack, which is actually the Fortran library that's underpinning what SciPy uses. So we found a set of hard benchmark problems. There's a group that's published these hard benchmark problems. And it turns out that the MinPack only solves 21 out of 23 of these problems. And we were able to work on some new methods for trust region, new trust region heuristics, and also new line search heuristics that was able to be a bit more robust and solve all of them on the first pass. You can check this out at SciML benchmarks if you search for it. We keep a basically as part of our continuous integration process. We keep a benchmarking server going that is then generating all these benchmarks as we go along. And we're now looking for some more difficult benchmarks to add to the system because we got a full win on some of our methods, right? So we're currently adding new harder problems in to be able to get some more losses. But our current state is that we tend to have some pretty robust solvers. And how fast does it end up being? Well, I think to really understand the performance difference here, one way to understand it is to look at this tweet that came out of MathWorks, right? They described how for this nonlinear solve problem, it's an interval root finding problem this time. They said, okay, we went from 5.8 seconds to 1.66 seconds on a recent MATLAB, and they're proud of this benchmark. So what we said was, well, what happens if we do solve the same problem, right? So solving the same problem with roots.jl and Julia ends up being about 0.46 seconds, right, which is already 3 times faster than the 1.66. But this is roots.jl, not our new, smarter nonlinear solver. And when we try our new one, we get down to 0.06 seconds. And actually, my student was telling me earlier today that this is actually down to 0.005 seconds. There's an optimization that we have inside of here of details. So that should be in the next version, I think, coming out about next week. That we'll actually get another 3x on this case. But this shows you that the progression then of the timings by using different aspects of compiler optimizations. Nonlinear solve then is really flexible. So when we're doing these benchmarks, right, and how do we keep a CI system that is benchmarking, the Fortran codes and all of our new solvers and everything, we don't treat them as separate. What we've done is we made it so that way we also wrap all these same Fortran codes and the C codes, and we directly have the ways to be able to call them. And one reason for that is we just want to have every method under the sun. So this right here is really trying to show that there's just tons and tons of different solvers. I can't even show all of them in one screenshot. There's about, I think, like 40 nonlinear solvers, which includes wrap methods from Fortran and wrap methods from C, but then also new methods in Julia. And some of them are specialized to small equations, others are specialized to large equations, wrapping the other solvers in Julia as well. So everything possible we're putting in one interface, so we could just continually benchmark across all of them. Another big part of the flexibility too is alternative termination modes. So being able to be very clear about here, I only want to stop the nonlinear solve when I hit a certain condition, and there's a whole different set of conditions. These are resolved in a compile time, so it optimizes a lot of different pieces about how the termination modes are used, so that we can cut out some computations. So one of the nice things that we've really done with the differential equation solvers is we made it have automatic solver detection, right? A lot of these libraries for ODE solving, they say, oh, tell me what you want to use, a fifth order Runge-Kutta method or Radow method or whatnot. And we said, no, if we can actually inspect your function f, then we can actually probably figure out what a good method is for you. And we've carried this idea over now to NonlinearSolve.jl. So the syntax is almost exactly the same as the ODE case. You just define your problem and you call solve. And what it does is it uses these kind of poly algorithms now, which, so for example, these poly algorithms, what they'll do is, it's very easy in a nonlinear system to know whether you solve the problem or not, right? So it can do something that's like a fast method and say, oh, Broyden's method is going to be the fastest for large problems because you don't have to calculate Jacobians or whatnot. Let's try that for a few iterations. If it's not converging fast enough, let's kick out of that and go to some kind of Newton method. And so there's these kind of poly algorithms I can make use of by default that are choosing different combinations of methods in a way that's either trying to get the fastest version or trying to guess at what the fastest version is, or a super robust version, a version that is mixing a bunch of different robust methods. But these kind of poly algorithms, I think, are something that they don't really exist within a lot of libraries before nonlinear solve. But I think a lot of users of numerical libraries, you tend to go, well, if I need this to solve, I'm going to loop over a list of solvers, right? And these poly algorithms and the default algorithm is effectively doing a smarter version of loop over all algorithms and find out which one actually works, right? So it's kind of built into the system then how it's doing that, and how it has quick endings to be able to then know which one in a compute graph would be the next best choice, and things like that. Um, Everything here, just like with the other parts of SciML, are all GPU compatible, so it all works together with GPU computing. And we'll be doing some tests on the kernel generation aspects as well soon. And it supports auto batching. So if you want to solve many different nonlinear solve problems at the same time, putting a for loop over it versus using this batch form, it turns out that there's some batch optimizations you could do in the LU factorizations and such. And so we have some batching optimizations, which is similar to what we have in the ODE solver case as well. So that really means that what we've done with nonlinear solve is we really made it integrate with anyone who's using other parts of these libraries, the differential equation solvers or optimization methods, can effectively kind of almost brainlessly just say, okay, I'm just going to guess the syntax and do the same thing, and it should end up working, and you should get the similar results in terms of, okay, GPUs work the same way, and optimizations work the same way, and all these things are built to be the same. Now with this new nonlinear solve library that has the simplification tooling and auto sparsity tooling integrated into it, right? So it's not about just having the compiler integration, but it's also integrating the ecosystems together. I think that's an important part. Now, one of the last pieces is integrating scientific machine learning, right? So this is why we're SciML and not just SciPy 2.0. But and so what exactly is the scientific machine learning aspect? So what we do with scientific machine learning is we integrate the way that you do model building with machine learning to be able to effectively do machine learning with small data and do things like automate the discovery of missing equations within models. So what does that look like? So let's say you had an equation, and when you solve your equation and you check it against you check your solution again. You build your model, you solve your equation, you check it against real data. You don't actually have a fit, right? Your solved model is very far away from your data, right? So one of the things that we've been kind of showing in the ODE space is that if your model is far away from the data, what you can do is you can take your physical model, you can extend it with neural networks, and then use that to be able to find out what's wrong about your model. And then you mix that with some symbolic tooling to be able to spit out how you should be changing your code, what equations you should be adding to your code, such that it will then improve the predictions from your model, right? So it actually spits out code and equations for how to do this auto completion of your model. And in the ODE case, we've been doing this all the time, right? So here, for example, is with the LIGO black hole data. If you assume you know Newtonian mechanics and you are looking at binary black hole system, you can train on a very small amount of data and then be able to extrapolate and show that you've actually learned the relativistic corrections to black hole dynamics, right? And so this is something that we actually do standard now inside of our optimization libraries and inside of our ODE solver libraries. And we wanted to make sure that we had the same experience with nonlinear solvers. And what does that look like? Well, what that really means then is that if you were to, take a nonlinear system and put it inside of a loss function. So you say, I define a nonlinear problem and I solve it and I do something with it against data inside of a loss function. If you do things like forward mode automatic differentiation or reverse mode automatic differentiation over this loss function, it will just do all the optimizations that are required. So it'll make use of these kind of implicit adjoints or implicit differentiation rules. It's doing this automatically behind the hood. This is the optimal code for this problem. And so what that means is then, all the things that you'd want to do with, say, backpropagating, neural net, this F then can have a neural network inside of it, and it will know how to automatically backpropagate this F that's defined by a neural network that's inside of a loss function of a nonlinear solve, right? So all of these things then compose seamlessly. And we actually demonstrated this fairly recently in something called deep equilibrium networks. This is a case where you try to find the U such that a nonlinear neural network of U equals 0. Right? It's a nonlinear solve root finding problem that's defined by a neural network, and it ends up having some nice properties. They're effectively infinite layer neural networks because they're neural networks that are taken to the to the point where if you're to do another application of this neural network, you get the same result. So it's a infinite layer in a very well defined sense. Um, and we showed that we can actually improve a lot of other ways of doing DEX just by using a explicit approach with the implicit approach. You can read the paper for details, but effectively this was all done with nonlinear solve. This was all done in a way that gives you about 8 times faster than the vanilla DEX and everything, using this new nonlinear solve library. And all that we did was we just took a neural network, stuck it in the right hand side, used the nonlinear solvers, and now the standard nonlinear solvers of Julia are the ones that you would use to kind of do these special machine learning layers, right? There's no special separate machine learning library to learn. The standard tools of Julia all interconnect with machine learning and with all the other tooling that we have around there. And yeah, that's what I wanted to kind of show. So in the end, what we started with was we started with this idea of we want solvers that are getting rid of the black box and using everything about our compiler analyses to automate the way that we improve solvers. But then what we did was we didn't just leave it at that as an academic exercise of is this possible, but now we did everything that was then required to make it be interfacing with all the other tools in Julia, so that way it would really look and feel as a new standard. And yeah, hopefully we hope that this then becomes the new standard within Julia, because we believe that this has a lot of advantages over some traditional ways of building and writing and building nonlinear root finding libraries. So yeah, thank you very much.
All right. If there's no further questions, just want to give a huge thank you to uh, Chris for this talk today. Um, Amazing job. And thank you all attendees for joining. This is the last day of PyData Global 2023. We hope you enjoyed everything. There's one more talk happening now, I believe. But other than that, this is the end of the general track for PyData Global Day 3. Thank you all for attending so much. Chris, once again, thank you for speaking. And yeah, we hope you enjoy the rest of your day, night, wherever it is you're hailing from. Thank you all so, so
Yeah,
much.
thank you very much. And oh, there was a question that was this was very informative. Will you be posting the slides? Yes, I will be posting the slides. If you get in touch with me via LinkedIn, that might be the easiest way, and I'll probably be posting the slides right afterwards on Figshare. So yeah, stay tuned for that.
All right. Thank you so much again, Chris. Take care, everybody.
Thank you.